All right, so tonight we're going to cover the central limit theorem and confidence intervals. The goal for tonight is to get kind of an intuitive understanding of the central limit theorem because it's super important to basically all of statistics from here on out. And then we'll go into some confidence intervals, both when we know the population standard deviation and then also using a t-distribution. So the central limit theorem is basically summarized with this. The distribution of sample means is approximately normal given enough samples and despite the underlying distribution. So to kind of show this, there's some features involved with the central limit theorem. So the means of the sample means will approximately be the population mean. So if we take a bunch of samples, calculate all their means, and then take the mean of those means, that will almost always be almost the same as the population's mean. Similarly, the variance of those sample means will be approximately equal to the population's variance divided by the sample size. So to kind of show how that works, we'll import some libraries here. And then we're going to create 4 different distributions of different shapes and sizes. So we're going to do a normal one, a uniform one, an exponential one. So just to give you an idea, an exponential distribution is related to the Poisson distribution. So Poisson tells you, given a lambda, it tells you about how many times you'd expect a certain event to happen. Exponential tells you how long it will be until the next event occurs. And you'll see what it looks like here in a second. And then the beta distribution, it's kind of hard to explain. It's basically used to predict probabilities of probabilities, if that makes sense. But you'll see what it looks like here in a second. We'll go ahead and plot all 4 of them. And so there you have it. So exponential is just kind of like a logarithmic graph. And then beta, given the variables we put in, it takes an alpha and a beta parameter. And making those the same gives it this kind of U shape. So we have a standard normal distribution, and then we have 3 that are not. So we're going to test out those 2 features about the sample means and the sample variances with all 4 of these. So this here will create a data frame that has the means of all of those populations we just made and the variances. And you can see them printed out there. All right, so now we're going to take some samples for all 4 of these. So what this does is basically we set our sample size and the number of samples we want to take. So we're going to start with just a sample size of 10, and then we're going to take a group of 10 samples 50 times. So for each of these, it's basically doing that. And then it's calculating the mean for all of those samples for each of those distributions. And then we just add them all together in a list here at the bottom. So with that, now we can plot those sample means for each of those distributions. And you can see that despite 3 of the original population distributions being non-normal, the distribution of the sample means tend to become normal because of the number of samples we took. So now if we insert those sample means and sample variances into our data frame, we can kind of compare. So our means should be equal to our sample means according to that first feature, the central limit theorem. And we can see that most of them are kind of close. They would basically get even closer if we increased either the number of samples or the sample size. And then the variance should be the population variance divided by the sample size. So to test that, we can calculate our expected variance by dividing the population variance by the sample size and adding that to the column. So we can see that for some of these, they're kind of close, except for actually the normal distribution, which is kind of weird. But if we would take another set of samples, if we would increase the sample size or number of samples, we would probably see a value closer to what we expected. So to summarize, the more samples you take and the larger the samples are, the closer to a normal distribution the sample means will be. And that's basically the central limit theorem in a nutshell. So using this, we're going to try to solve a problem now. So the Scoops Ahoy corporate wants you to estimate the average annual revenue for all of its shops. They tell you that the standard deviation of revenue is $50,000. Also, they recently sampled 30 stores and calculated an average annual revenue of $50,000. If they want to be 92% certain of the true average annual revenue across all stores, what interval of revenue should you give them? So to do this, we have to talk about confidence intervals. So if you recall on the normal distribution, you can basically divide up different percentages of the graph in terms of standard deviations from the mean. So for example, 68% will fall within one standard deviation of the mean, so on and so forth. This kind of breaks it down. So we can use that to determine a confidence interval around the true mean. So first we have to find what's known as the Z critical value for the given confidence level. So in this case, say we wanted to find for a 95% confidence interval. You use stats.norm, and then PPF is basically the inverse of CDF. So the cumulative distribution function, it would give you a percentage, but the PPF, you input a percentage, and it gives you the number of standard deviations away from the mean. So you would think that you would just pass in 0.95 if you were looking for a 95% confidence interval, and you would get this Z-score. But that's actually wrong. So Python does something weird with this library. When it calculates this, it only includes the left tail. So what you actually have to do is adjust it a little bit. So you take what confidence interval you're looking for, or confidence level, 95%, and then you have to add 1 minus that confidence level and divide by 2. I can give you some like graphs and stuff that has this make more sense, but in general, it's just to accommodate for Python only looking at the left-hand side instead of both the left and the right side. So if we run this, we see that actually the Z-score for 95% is 1.959. And this kind of shows it here. So we want the area in between those two Z-scores. So let's see. So for 68% confidence, we would do this. We plug in the percent confidence we want, and then we add 1 minus that percent confidence and divide by 2. And so that would be 0.99445. So to go back to our problem here, let's see. We want a 92% confidence level. So we need to calculate our Z-score here using that same formula. And we get 1.75. And then the margin of error. So the distance from the mean on one side is equal to this equation here. And that is our Z value times sigma, which is the standard deviation of the population. And then we divide by the square root of n. So we can go ahead and plug in these values that we know here. So let's see, sigma is actually 50,000. And the number of stores they sampled was 30, so n is 30. And then the margin of error is just going to equal our Z critical value times sigma divided by the square root of n. So our margin of error is about almost 16,000. So now all we do is we take our sample mean, which was 450,000, and we subtract the margin of error on one end, and then we add the margin of error on the other end. So then we get the upper and lower intervals around that mean. And so we can say with a 92% confidence level, the average revenue is between about $434,000 and $466,000 per year for the stores as a whole. So using that, we're going to go into a short activity here. We have 2 quick questions. It shouldn't take too much time. I'm going to go ahead and pause recording.
So for number 1, I pulled in the Pokemon sample CSV. They gave us the sigma as 15. The confidence level 85%. For N, I just did the length of the sample. I found the average speed by just doing the mean of all the speeds in the sample. I used the Z formula to use this confidence level plus 1 minus the confidence level divided by 2. And the margin of error was just Z times sigma divided by the square root of N. So I got the average speed between 59 and 66 at an 84% confidence level.
That looks good to me.
Okay, cool.
All right, so then the second question, who wants to take that?
I'll hand over controls.
I guess I could try it, but I don't. And looking at what Jacob had there, it does not look like what I have, so.
We'll help you through it.
Me either.
Okay. All right, let me share. This one. Okay, so it said that there was a confidence level of 90. So in order to get the Z score, I did this, right? So subtracting the confidence score from 1 and then dividing by 2. From what you said, I figured in order to get the margin of error, just subtract the upper and the lower from the mean. And I got, sorry, let me show what I got there. And when I did from 25 plus 7.5, I got the same number. So I figured that I was somewhere along the right path. Right, and then the sample was 30. So what I did is I just rewrote the formula in order to get sigma by itself, which was the margin of error times the square root of N divided by Z, and this is what I got. I don't know.
Okay, so go back up to the margin of error calculation there.
This one?
Insert a cell above that, yeah.
Okay.
So first, let's calculate the mean of the sample. So we know that the lower limit on the interval is 25 and the upper is 40.
Right.
And we know the mean's in the middle of that. So how would you find that middle point?
Add.
Yep.
Add and divide, and I subtracted for some reason.
Yep, there it is.
Okay.
Okay, cool. So that's your mean.
Right.
And then your margin of error is the distance from that mean to either interval.
So then I have to do 32.5 here. So that's that. So I just mixed up my numbers and I got that.
Let's see. So the sigma is going to be equal to the margin of error times the square root of N divided by Z, which is what you have there. That doesn't matter, actually. That should be fine.
Okay.
So I believe that looks right to me. Beth and Jacob, is that close to what you got?
I got 24.97.
Hold on. I'm working on it.
Jacob, can you see like anything you did differently?
That's what I'm checking for now.
Why do I keep subtracting the values to find the mean? That doesn't even make sense.
I just did the same thing, Julia. You're good.
Well, what you basically did was found the margin of error. That's another way to find it. So
Maybe that's what I was going for. Who knows?
I don't know what I did different. Yeah. Let me try this.
So the margin of error, once again, is just when the distance basically is the distance from the mean, from one interval to the next, right? So
right. So, you know, as the confidence level gets higher, that distance around the mean is going to get larger. Because for us to be really sure, we're going to have to cast the net really wide. But if we would have a low confidence level, then that would be a little bit narrower.
okay.
I got a different number for mine.
Okay. Do you want to share your screen and show us?
Yeah. This one. Okay. This is what I have going on. So I set up my n and I set up my sample mean. Thanks for the pro tip to make sure that's added. Then I calculated my z, and then the margin of error is just 40 minus that sample mean, right?
Mm-hmm.
And then, like Juliet, I rewrote my margin of error equation that we used up here. I rewrote it to where everything would equal sigma.
That also looks right calculation-wise. Jacob, did you get 24 as well?
Yeah. Well, I got the 32.5 for the average, the 7.5 for the margin of error. And I just don't know why we're getting different numbers.
Julia,
So,
do you want to run yours one more time? Just make sure you do it in order.
so
I feel like something maybe just got out of place.
I made sure that I put parentheses around here so that this would be done first. I can see that being a possible difference.
Actually, I don't think that would make a difference because order of operations, it would be the same either way.
I don't trust it.
Please
If
exceed.
you were adding them, it would.
Right.
I think I figured out what my problem is. I got to define my n, and I think that my n was not being defined before.
That would do it.
24. Got it.
All right, cool.
It was taking
So,
the
yeah.
n
From that first problem. Yeah.
That makes sense. All right, so I will go ahead and share my screen again and we can move on to the next part here. All right, so in those cases, we knew the population standard deviation. But if you think about it in real life, when would we ever know the population standard deviation but not know the population average? Doesn't really make sense. So in real life, most of the time you don't know the population standard deviation and you instead only know the sample deviation. So in that case, you have to use what's known as a t-distribution. So this here is a chart of different t-distributions and then also the normal distribution. So in general, t-distributions are a little bit shorter and fatter than the normal distribution. It basically accounts for some of the uncertainty since you're using the standard deviation of the sample and that might not be the exact same as the standard deviation of the population. But you can see as you get higher sample sizes, the t-distribution will start to approach the normal distribution. So to take the standard deviation of a sample, you have to use a slightly different formula. It's almost the same as normal standard deviation, except instead of dividing by n, you divide by n minus 1. You do this because it helps to account for small sample sizes. So when n is small, this has kind of a large effect on increasing the total standard deviation. But when n gets really large, subtracting 1 from it doesn't really make a difference. And it will be almost the same as if it was just n. All right, so to do this in Python, we can read from that Pokemon sample CSV we just had and just grab the speed column. And if we want the standard deviation of that sample, we can do the standard deviation from NumPy, but then it has this difference degrees of freedom argument. And that basically means n minus x. So whatever you put in here will be the x. And in this case, we want n minus 1. So we have to put a 1 in there. So if we run that, then we get the sample standard deviation or the standard error of 26.788. So now that we can use the sample standard deviation, we can do confidence intervals for a t-distribution. So again, the margin of error formula is almost the same, except now we use a t-score instead of a z-score. So consider we have only the sample of 30 Pokemon. What is the 90% confidence interval for the average speed of all Pokemon? So this time we're going to ignore anything we know about the whole population. We're only going to focus on what we're given by the sample. So to do this, we first have to calculate sigma. So we take the standard deviation of the sample and we divide by the square root of n. And then, actually that's not sigma, that's technically what's called the scale. And the reason we want that is because first we're gonna calculate that interval using a different method. So it's in the same library, stats, and then t for t-distribution, but we can actually use the interval function itself. And so we pass in alpha, which is the confidence level, the degrees of freedom, which is n minus 1, so it's our sample size minus 1. And then the LOC is basically the mean, so we pass in the mean of the sample. And then the scale is actually the sample standard deviation divided by the square root of n. So it's basically just those two parts of the margin of error formula combined together. So if we run that, we get this interval here. And then to check it, we can do it the old-fashioned way and basically just use the t-distribution and then do ppf. And then we can pass in the confidence level we want, adjusting for Python only choosing the left tail. And then, let's see, we pass in our degrees of freedom here. So before, for the normal distribution, we don't have to pass that in. But for a t-distribution, you have to pass in the value for n. And that is just the length of our sample, the sample size minus 1. And then according to the formula, we just multiply by the sigma, which is the standard deviation of the sample. And again, we have to set the DDOF, difference degrees of freedom, to 1. And then we divide by the square root of the sample size. And then if we add that margin of error and subtract it from the mean, then we should get the exact same answer as using the interval method. So you can do it either way. It's probably easier to do it with just the interval, so you just do it all in one line. But you can always check your answer doing it the longer way. So now we're basically going to do what we did before, but now for t-distributions and without knowing the population standard deviation. So I have 3 problems here. The first 2 are actually using your data set from the first mod project, but instead I took a sample of it. So you're going to calculate some stuff around that. And then the last one is kind of a tricky one, like the second question from before. And so I'll go ahead and pause recording here.
Alrighty. So using the sample data from King County and a 95% confidence interval, we just pulled in the price from the CSV, the sample CSV. We figured out the scale of that CSV, and we passed it into the interval function here, or method, using the alpha as 0.95, the length of the sample -1, the mean for the LOC, and the scale we defined here. So I got, what, 420K to about 563K.
That looks good to me. Is that what everyone else got?
Okay, I have a question then. Then I guess I did it wrong. The scale equals to scale is what the scale, okay, no, hold on. Give me a second. Because before it had said sigma, but it has to equal the scale that we have, right? That we did.
Yeah, so the scale is basically the sigma divided by the square root of n.
I see. Okay, hold on. I did that.
Alrighty. Y'all still need it?
No, I think you're good. Juliet, do you got number 2?
I got parts of it.
That works.
Okay. I don't even remember what I'm. Okay. So I got this. I did the same thing as before, where we read in the bedrooms, and I did the scale, but this time I did scale 2. And so in this case, the confidence interval was 90%. So I did 90 for the alpha, and then did the sample -1, then the mean, and then in this case it was scale 2. So this is the interval that I got for that. Same situation for the bathrooms. So I just wrote in the bathrooms, and then scale 3. So then I changed this to a scale 3, and then I got this interval. And so before, what I had done was subtracted the intervals and tried to see which one was the smaller amount, and that would be the one that was tighter, right?
Mm-hmm.
So, but I didn't get to that because I had it wrong, so I couldn't fix it yet. But I don't know. It looks like the one that would do it was, just by looking at the numbers, it looks like maybe bedrooms.
Yeah, so if you just set equal to that whole stats.t.interval, if you set like x comma y equal to that, then x and y will be those two interval values, and then you could just do like y minus x.
Say it again.
So so there put x comma y, since you're getting two values back, and then set that equal to that. And then down below, if you just do y minus x.
But if I do that, okay.
Oh yeah, yep.
And then, so here I could do y minus x, right?
Yep.
And then this would do the same thing here, and I'll just pick something else, right?
Mm-hmm.
And then this would be B. And then this one would be B minus A. And then I gotta change this. Oh, it's still bathrooms?
That's what I got.
Okay.
Yep.
It's still bathrooms. I was right the first time, even though I was wrong. Got it.
So basically what that means is that the interval around the population average for the number of bathrooms is tighter. So we're basically like kind of more sure where it lies. All right, so then number 3.
Okay. Okay, so this is what I got for number 3. The first thing I did, I set all the parameters they gave us in the problem up, and then I solved for my mean first. Then I solved for my margin of error. Then I put this in to calculate for my t-value, and I went ahead and set everything up to calculate for n. And this is kind of when I was like, oh, I need the sigma. I need the standard error for all of this stuff, but I hadn't ran this cell yet. So if I had the sigma, I'd be able to plug it in, and even if I got that, I would still have this error, which is the degrees of freedom. And this is the n-1 part of the equation to calculate for stuff. It's basically how many samples you have.
Yep. So basically the problem is impossible since each t distribution depends on the number of samples. So since we don't know the number of samples and we don't know the t critical value, we basically can't solve the problem as it is.
So I went with this one because I knew that this one here, this t interval problem, had the length in it automatically.
Mm-hmm.
It's part of what you have to pass in. So I went with this one, just stats.t to get the t distribution, because I didn't know that you had to have I didn't know you had to pass in the number of samples.
Yep. All right, cool. So that kind of concludes everything for this lesson. Hopefully this gives you all a good foundation for next week when we start with hypothesis testing. That's going to be a huge focus for this mod, especially because your final project for the mod is a whole bunch of hypothesis testing. So definitely study up on that before the lesson, and you should be good to go.
All right.
I'm going to go ahead and stop recording.